I'm thrilled that we have Shaun Barker joining us today. So he'll be chatting to us about identifying cryptic alteration around carbonate-hosted ore deposits with a case study from the Mount Isa copper deposit. So thank you so much, Shaun, for joining us. It's wonderful having you.
Thanks very much, Jess, for the invitation, and hello everyone, wherever you are in the world. Good morning to you back in Australia, or if you're on the eastern side of the Pacific, good evening. It's great to be here. So today I'm going to try to do, I guess, a bit of a high-level summary of something I've been working on for a long time. And this picture here has absolutely nothing to do with any ore deposit that I'm aware of. This is actually my PhD field area near Wee Jasper in New South Wales, and I studied carbonate or fracture control, fluid flow through carbonates as part of my PhD with Stephen Cox at ANU. So I've got a tortured background of structural geology and geochemistry, so I should probably be a lot more antisocial than I am. So in this talk, I'm going to give you sort of some high-level summary of some of the work that we've been doing for a long time, and then present, I guess, a case study from the Mount Isa system, which I think I caught the tail end of Greg talking about some of the history there. We're built upon some of the early work that had been done there by Chris Waring and some of his colleagues at Monash to really sort of, I guess, prove up some of the theory that had been kicking around for a long time, and we'll sort of finish off on that. So I'd just like to start off with some acknowledgements of people who've worked with me over the years, and this doesn't really capture all of those people, but it's some of the key contributors, particularly to this talk. Colleagues here at UBC, Greg Dipple and Ken Hickey, Andreas Beinlich and Craig Hart, who were part of an earlier MDRU project, and more recent collaborators down at the University of Washington who did some of the clumped isotope work, which I'm just going to touch on for a couple of minutes towards the end of the talk here, as well as some PhD students, some of whom didn't suffer for a particularly long time. Ben suffered for a little bit longer, and I'll be presenting some of the results from their PhD theses that have all now been completed. So I don't really need to tell this to any of you, but you know, why do minerals matter, and particularly why do I think about and work on carbonate-hosted ore deposits? Well, this graph, which I saw ironically enough from the BP website up to date sort of about 2 or 3 years ago, shows you the sort of global energy demand. And the challenge that sits in front of us at the moment is that little thing there that's flashing was the world's basically renewable, and I've captured in there the nuclear, if we want to look at nuclear as being a low carbon emission source, or renewable depending on your point of view, source. And of course the rest of this is the energy that the world consumes. So somehow over the next 30 years we have to grow this slice of the pie that is flashing in here to basically be the rest of that pie. And that, of course, is an incredible challenge, because almost all of that energy is going to have to become electrical in nature, or much of it will become electrically delivered. And to deliver that, we have to do it through minerals, through copper, through storage, through transition to battery-powered vehicles, etc. So, you know, there's a massive challenge that sits in front of us. And we can, of course, look at the numbers on this, and we see, you know, projections, and depending on your favorite, you know, paper of the month or person talking about it, and the numbers get knocked around. But we're literally talking about mining, you know, thousands of % more of a huge number of minerals. Cobalt and lithium are often at the top of the topical discussion list, but copper is probably one of our biggest challenges, just in terms of the sheer amount of copper that we need. Some of these percentages are probably a little bit misleading in terms of the actual sheer volume of material that we need to find, but copper is really one of the biggest ones. And so one of the reasons why I'm interested in carbonate-hosted deposits is that they host, you know, a variety of different ore deposit styles, including very important copper deposits, either as skarn or as, in the case of Mount Isa, sediment-hosted copper systems, or metamorphic style copper systems, depending on what basket you like to throw them in. And these styles of mineralization in these systems mean that they're often quite difficult to explore and vector through, and we'll touch on that in a minute. So there are a number of different deposit types that form in sediment-hosted environments, particularly carbonate-hosted environments, and the tools that I'm talking about today are probably broadly transferable across many of these, although they're all going to have to be applied in somewhat different ways. And those ore deposit models that we develop as scientists and of course as industry practitioners become really important as we think about how we integrate these tools with them. So what are the challenges and why do I mine in carbonate-hosted deposits? Because they often have what is often referred to as cryptic and relatively narrow alteration signatures around the ore bodies. So if we compare these to, a porphyry or perhaps a volcanic hosted massive sulfide system, where you might have alteration halos on the order of kilometers, that a well-educated geologist can recognize the different mineral alteration assemblages and figure out where they are relative to the heat source, relative to the likely porphyry and causative intrusion. In the case of carbonate-hosted systems, we simply don't have that. We often have very difficult to recognize mineralogical changes, particularly more distally to the ore systems. And that's because the carbonate rocks are incredibly reactive. They neutralize acid and they tend to suppress the alteration that we see. And so in this talk, I'm going to touch on new tools, which in some ways are really rehashes of old tools that we've been looking at to improve both our understanding of how some of these deposits form, and particularly in the context of this talk, thinking about our ability to vector towards ore deposits. So to highlight the sort of challenge, and perhaps this is the most extreme example, this is where I really cut my teeth as a postdoc, moving from a completely academic PhD into quite an applied postdoctoral fellowship at UBC, was looking at the footprints that surround the Carlin-type gold deposits, at the time most famous in Nevada. Since the time I worked on them, have been described in various styles and now a number of other places around the world. So these are carbonate-hosted, cryptic gold systems, and I'm cheating a little bit here to give you a really extreme example. But on the sample on the left-hand side, running a pretty healthy gold grade there, 25 ppm, or almost an ounce per ton. The sample on the right-hand side of this image is essentially background. And if you look at this as a geologist student looking at this photo, you have a really hard time telling that there's much of a difference between them. The bedding structures are preserved in both of them, running, I think you can see, hopefully you can see my mouse running up and down the screen. You might see there's a little bit more sulfide. Some of that's probably actually diagenetic sulfide that you can see, pyrite that you can see in here. This is genuinely referred to as invisible gold. You can't see it, it's all gold within pyrite. Now, if you, of course, cut a thin section, you go zooming on, and then we start to see some bigger differences. You can see all these little speckles in here. These white speckles are those auriferous pyrites. But if you're looking at them as a geologist, you have a really hard time seeing that. There certainly won't be much carbonate left in this rock on the left-hand side. All the carbonate's been dissolved. The rock on the right-hand side will probably fizz quite vigorously. But otherwise, it's very difficult alteration to map in core. And you really are reliant upon your chemical assays, your gold assays to delineate the ore zones, and your pathfinder elements, and some of the other major element chemistry to help you figure out what sort of rocks you're sitting in. It's not the sort of thing you can log out in the field and say, oh, this is going to be high grade, or this is going to be low grade or background. It's incredibly difficult to do. So not only is it often difficult to pick the alteration often doesn't go very far at all. So this is an example from some work we were doing with Mag Silver, who one of their main technical geologist leader is Peter McGaw. Peter's a world-recognized expert on carbonate replacement systems and skarns. This is a major type of deposit that Mag Silver were targeting. And we did a study with them at MDRU that was published a couple of years ago in economic geology on the CINCO to MAYO project. And this was a very interesting study. Peter got us involved because they were trying to explore for CRDs and ultimately a large skarn system and hopefully a porphyry system. And the problem that they encountered was they had mineralization in almost every hole, low-grade mineralization, sniffs of systems. And so they were looking for a tool that would help them vector towards the main fluid upflow zones. And just to show you the sort of problem that you come across as an exploration geologist, this is one of their major discovery holes just before they lost access to the property in about 2012. And we can see here we're down about 800 meters depth, and we're drilling through what look like very boring limestones. There's a little bit of sort of marbly looking stuff kicking around, but otherwise this looks almost exactly like that outcrop that I showed you in my PhD from a PhD. It's just there's been a drill hole punched through it instead. There's various carbonate veins. Does this have anything to do with a mineralized system? Well, if you step that hole down about another 150 meters, you drill into some pretty high grade, thick zone of massive sulfides associated with probably starting to get a fairly sort of proximal CRD type system and perhaps getting close to a skarn. So in that 150 meters, we've gone from a bunch of relatively sort of barren, boring looking limestone with nothing to log. There's no key alteration minerals that you could log into high grade, multi-meter, high grade silver, some gold, a bit of copper, lead and zinc. Very typical for these carbonates hosted ore deposits. Narrow alteration halos, difficult to log. Now there are of course tools that we can use to help us. These are some pictures courtesy of Andrew Steiner, who's a PhD student just finishing up here at MDRU. Andrew's been using ultraviolet fluorescence imaging, which is very, very old and pretty standard industry technique for carbonate-hosted deposits. And this is really a great tool to get some spectacular colors, which is one of the reasons to show you this, is just these beautiful photos with these fluorescent calcites of all sorts of different colors. And often when you get more proximal to carbonate-hosted deposits, you'll start to pick up these UV fluorescent veins, which are typically responding to elevated manganese concentrations. Now, the challenge with this sort of visual technique is that if you have any sort of iron-rich carbonates, that iron, even if you've got high manganese, the iron will quench the fluorescence. So this is a very useful qualitative tool, but it's also pretty easy to fool. And in fact, if you try to apply this at Mount Isa, which we certainly tried to do some UV fluorescence on some veins, it's all ferroin dolomite, high iron dolomite, and they give absolutely no UV fluorescence response, whether you're close to ore or miles away from the system. So it's a tool definitely with applications. However, hydrothermal systems have a number of different features or signatures that we can recognize and try to map. Now, some of them are obvious. Things like the metal signature, the major elements associated with our hydrothermal systems are something that we're pretty good at geologists as logging. We can see chalcopyrite, we can see skarn minerals, we can see potassium feldspars when we're in the guts of the system. However, as we start to move out of that system and we move away from the region where the metals and the major elements are being mobilized, we start to run out of things that it's easy for the human eye to pick out, and we run into things that are a lot more cryptic. We might see volatile or alteration driven by volatiles, propylitic style alteration, where we're simply putting water or carbon dioxide into the rock. You might get some bleaching or oxidation in some of these carbonate-hosted systems. And we get significant isotopic alteration, which I'm going to touch on today, some of the work that we've been doing with that. And one of the ultimate things that we should see in these systems, if we had a reliable tool for measuring it, is the thermal footprint, the heat signature. By definition, we're looking at hydrothermal ore deposits, and the clues in the name, hot water. And so if we could map heat in these systems, which Ken Hickey, my former supervisor at UBC, did in the Carlin systems, work that Greg Hall was involved with in the 2000s when he was working for Placidome, this was a very powerful tool in some hydrothermal environments if we have better tools for mapping heat. So to give you an idea of what this looks like visually, this is one of the models that Ken and the research team at UBC came up with what do the alteration patterns look like, in this case, around a Carlin-type deposit, although I'd argue that similar patterns will exist in many carbonate-hosted deposits that we look at. We have, of course, here some ore. That's what we're hoping to find. That's what we hope our geologists are good at recognizing, and some deposits it's easier than others. in the gold, and then around that in the purple color, you've got some sort of mineralogical alteration. In the case of Carlin deposits, that would often be manifest as carbonate dissolution, as silicification, so you get hard, you lose the carbonates, you use your HCl, it doesn't fizz anymore. You scratch it, it's hard, it's full of quartz, often full of sulfide. The rock's actually quite smelly. The nose can be quite a good tool in Carlin-hosted deposits. But often over a matter of simply meters, that mineralogical alteration will disappear and there's nothing left to log. However, around that, at varying scales, we do get what we refer to as cryptic or invisible halos that you need a tool to help you to recognize. And in this case, one of the largest halos that we see is the oxygen isotope halo in the carbonate host rocks. And then surrounding that at some scale, and the reason why we've drawn this big gray blob is that this is the heat anomaly, is that the thermal aureole around a upwelling hydrothermal system will not only be in the flow paths, which is what these zones here are trying to show us, and this is a fault and this is a lithological layer that the fluids are chasing along, the overall zone around this whole system will heat up. And the analogy for this, if you go on at home and turn on a hot tap and you wait a couple of minutes and you put your head under the hot water, or your hand into the hot water, then depending on the water temperature, it might be pretty hot, you might get burned. That's you're being burned by advection. Now, if you grab the tap with your other hand that hasn't been burned and hold on to the hot metal, then you're being burnt by diffusion. And so that's the analogy here, is that the heat signature should be one of the largest signatures that we would see in these deposits. And the theory to explain this is something called reaction fronts. Now, this theory was developed in essentially the late 1980s and early 1990s, and it's been applied to a number of different systems. And one of the I guess best understood systems that it's been applied to in the economic geology world and mineral deposit world are skarn systems. So the idea here is that you have reaction fronts, and reaction fronts migrate through rocks over time as you react that rock with a fluid of some kind. So in the case of a skarn system, of course, we're taking a marble or a sedimentary rock that we're bringing hot magma into contact to, and then we're flushing hot water out of that magma, which is what this beaker at the top is doing, and it's flushing water through the rock. And as it does that, it causes a series of reaction fronts to propagate through the system. In this case, this reaction front that we're seeing here is the squiggly line, is the interface between marble and the skarn minerals. But there are actually details that I won't get into in skarn mineralogy that can be mapped out that tell you where you are in the system. Am I at the top of the system where my ore will be forming, or I'm in the bottom of the system where all the fluid has reacted away and has reacted with the rock, and I'm now dealing with it with an exhausted fluid. So we can use this reaction front theory, and we can map reaction fronts, which could be mineralogical, they could be geochemical, they could be stable isotopes, or they could be thermal fronts, to understand where we are in a hydrothermal system and to vector towards the ore body. They may also help us understand what are the permeability pathways controlling fluid flow. Are they faults? Is it lithological pathways? Is it a mixture of the two? So these are some stable isotope diagrams that have been put together by Greg Dipple, a colleague of mine here at UBC. And this is showing you what the theoretical reaction fronts look like for oxygen isotopes. So the idea here is on the left-hand side of the diagram, we flush fluid from a reservoir into our rock, and that fluid reacts with the rock and causes an isotopic anomaly to form. The reason why that anomaly forms, and I'll touch again on this in a minute, is that hydrothermal fluids have a distinctly different oxygen isotope composition to carbonate host rocks. So if you flush a fluid through a rock, a hydrothermal fluid through a rock, you will leave behind a stable isotope signature, along with all of these other signatures that I've already touched on. And so we can use this in a number of ways. One of the most important things that comes out of this theory and comes out of these calculations is the recognition that the more water you move through a rock, the larger the reaction front will move, the further the reaction front will propagate, the larger the size of the alteration halo. And that becomes a very important proxy, because if our fluids are limited in the amount of metal they can transport, they're metal undersaturated, then the more fluid you move through a rock, the larger the hydrothermal ore deposit that you could form if you've got the right trap rock. So this theory, this prediction becomes a very powerful one if it's true. And there's a lot of evidence out there from the studies that we and other people have done, including Chris Waring, who pioneered the isotope work at Mount Isa, that this theory absolutely holds up, and it can be used to predict the likely size of a hydrothermal ore deposit. So to try to give you a visual on this, here is a very low temperature, I hesitate to call it a hydrothermal system in Nevada, that I visualized a few years ago when we were doing some field work. In May, in the spring, we'd had some fairly unseasonal snow, and there was some snow melt forming from the sunny side of the hill, and the snow was flowing down the hill. So what we're going to see here is our unaltered snow, and it's going to get progressively altered by the snow melt. So hopefully you can all see this video. You can see the fluid is flowing down the hill, and there's a reaction front that exists that moves over time, and it's moving a lot more rapidly down the hill than across the hill, because the fluid flow is flowing from obviously the top of the hill downwards, driven by gravity. So here we're seeing reaction fronts propagated much further in this direction here. So we have reaction fronts, we have our unreacted rock, and we have what we refer to as reaction sides. So this analogy, where you can see here the analogy of a snow melt, think about that analogy being transferred into a hydrothermal ore environment and what you're going to map in these systems to see these fronts. And so the reason why oxygen isotopes are so powerful, I'm not going to give you much isotope theory, which I'm sure will be of a great relief to most of you, is that the waters that we see on Earth, whether they are meteoric waters, magmatic waters would be about here, ocean waters, all of these compositions are significantly less than the typical composition of marine carbonate rocks that have formed over the last 2.5 billion years, which mostly sit between about +20 and +30 per mil on the VSMO scale. Meteoric waters sit from around 0 +5 per mil down to -50. Ocean water by definition is 0. Magmatic waters are about 10. So there is no way that you can flush magmatic or hydrothermal waters through a carbonate rock without causing isotopic alteration. It's pretty well, it's almost impossible to achieve. So this is a very robust tool or a metric for alteration. And we've already been through that, so we'll skip over that theory. Now you can take the one-dimensional theory that I was just showing you. You can actually do this in 2 dimensions. So you could think of this as now a map or as a cross-section. And we have fluid that's moving here from the left-hand side of the diagram. The blue colors are showing you where the alteration is most intense. The red colors are showing you where the rocks are background. And what you could effectively do as an explorer, whether you had a series of holes moving through this, or you were able to pick through a series of outcrops, for example, in a carbonate-hosted terrain, is sample and try to visualize where you are in these systems. And one of the things to note is that as you go across fluid flow pathways, so the fluid's moving in this direction, this is a high permeability pathway, a fault or a lithological layer. When you're going across fluid pathways, the gradients are very steep. When you're moving down or along a fluid pathway, the gradients are generally much gentler. So this is what I mean by you can use this type of data to navigate within your system and figure out whether you're going across fluid pathways or are you going down fluid pathways. Now, one of the things that we did when I was at MDRU was we actually developed new analytical technology to try to bring stable isotopes out of, well, the 20th century, I guess it was, and into the 21st century. And we adapted some technology that had been developed for atmospheric science, for environmental monitoring, and modified it to analyze very quickly and cheaply the carbon and oxygen isotope composition of carbonate minerals. Now, we started off with what I call an auto student, which is a student who used to have to do this. And then after a while, we built an auto sampler that would enable us to potentially analyze hundreds of samples per day. So we're trying to both speed this up and make this cheaper to enable us to try to genuinely map these oxygen isotope fronts out in the real world. So not just getting 10 or 20 samples as an academic study, but literally collecting hundreds to thousands of samples and building up two-dimensional, and in the case of the work Ben did at Mount Isa, three-dimensional maps of oxygen isotope alteration. So these are some of the results of some early work we published in Economic Geology in about 2013 now, and I'm just starting to make myself feel old. And this, what you're looking at here is downhole plots of gold in the red in ounces per ton. These are sort of distal holes in Carlin-type gold deposits. And the blue lines you're seeing are some of our high density oxygen isotope measurements. So we're measuring oxygen isotopes in the same way that people do lithogeochemical assays. And what you can see preserved in these drill holes are what appear to be oxygen isotope fronts. Now, the data is certainly noisy, and we expect that from some of the theory. But what this data set here, for example, tells me is I was drilling down a structure that had fluid probably moving up it, and then I've drilled back across that structure again. So wherever this drill hole was, the structure, I've stepped back out of that at the bottom of this hole, and at the very bottom of it, the bottom of the isotope halo, there's a little sniff of gold. Nothing to get excited about, but perhaps it's telling you you're on the edge of a system. So this is a sort of theory and now being put into practice. We've got the theory, we can actually start to see these isotopic fronts. So now I'm going to step you away from the Carlin trend and take you to something much more proximal for those of you who are in Australia, which is looking at the Mount Isa copper deposits. So I'm not going to get into the controversy of the formation of Mount Isa. This session isn't long enough, and it's meant to be a session about geo-hugs, not geo-hatred. So we'll stick to having a reasoned acceptance in this case that the copper is most likely some sort of an epigenetic overprint on top of a syngenetic lead zinc silver system. I certainly think everyone would accept that the copper is later in the system, and the origin of the lead zinc silver we can debate about. Now, Mount Isa is a very mature set of deposits being mined for almost 100 years now, and the copper deposits that they're looking for are deep and they're high grade. So the grades can be, up to 3 to 5%. They're tight ore bodies that have relatively cryptic alteration halos around them. So these are tough targets. If you're drilling 1.5 kilometers or 2 kilometers, you want to get as much information out of them as possible. And so the following set of results that I'm going to show you are from the PhD of Ben Andrew, who was just finished up a couple of months ago, now working for Mount Isa Mines, applying some of this work. And he was following up on the earlier work of Chris Waring, which I must acknowledge Greg Hall for making me aware of that work, because it was well and truly buried in the literature, and I certainly wasn't aware of it. So there's a few too many words on this slide, but if you want to take the time to read them, you're more than welcome to. But I'll just concentrate here on the cross section on the right hand side here. So what Ben's drawn for me here is essentially I guess it's a schematic or integrated geological section through the middle of some of the Mount Isa deposits, showing you the sort of styles of deposits that we have. So the general model for the fluid for the formation of these deposits is that we have fluid coming from the Eastern Creek volcanics, almost certainly structurally controlled, exploiting some sort of structural architecture that is still debated as to exactly which faults were important and when they were active. And we formed a series of deposits either on that contact between the Eastern Creek volcanics and the overlying Urquhart shale, which is a dolomitic shale, so a carbonate shale. And we have some hanging deposits as well that have appeared to have exploited some structures to get well up into the hanging wall. Surrounding these high-grade copper ore bodies, we have what's referred to as the silica dolomite alteration. Now, the Mount Isa geologists have some nuances to this, particularly some textural nuances that they use to break these out further. But one of the major challenges with a silica dolomite is that it's quite variable in its extent. It can be tens or sometimes hundreds of meters from high-grade ore. And indeed, in some cases, it appears to be present with no ore associated with it. So it's a very useful visual tool, but in the case of this example here, you can see the 1.5 or 1.7% grade shell is almost at the same point as the edge of the silica dolomite. So you can be very proximal to it and see almost nothing visually. Now, when we start looking at the stable isotope data from Mount Isa, and this data set here is a collection of legacy data that was collected by Keith Hannon, who was a Mount Isa geochemist for a long time, as well as new data shown as the black dots that Ben collected. So the background Urquhart shale, the dolomites at Mount Isa, are something around 20 to 22 per mil in the terms of the oxygen isotope scale. And we can see that almost all of the rocks have been variably shifted off that, from shifted by a little bit to shifted to down to about 10 per mil, which we know is probably about the signature of the input hydrothermal fluid. So the rocks at Mount Isa have been heavily exchanged with respect to oxygen isotopes. There's also somewhat of a carbon isotope shift, but we don't have as good an understanding of what's driving that. Now, with the amount of data that have been collected at Mount Isa, both from new work that Ben did as well as from legacy activity, allowed Ben to actually construct a pretty robust three-dimensional model in Leapfrog. And this was following up on the work that Chris Waring had originally done, defining the size of this halo. So just to clue you in on what we're looking at here, so we've got these are map views. The ore bodies at Mount Isa are shown as these grey blobs in here. These are the main copper ore bodies, in this case projected to surface, I think. And then the colours you're looking at are the oxygen isotope anomalies. And what we see is a gradient in the isotopes from background, shown to you as the purple, moving to progressively more and more altered values the closer we get into the systems. Okay, so there's a gradient towards the ore deposits, and the size of the halo here is remarkable. So those are thousands of meters. So the overall isotope halo around Mount Isa is something on the order of, depending on how you want to count it, around 8 kilometers or so. So what we'll look at here is now a long section, and we'll just show you what the geometry of this now looks like in a cross-sectional, view. So again, that's just, we're looking at this long section here from north to south. So north is up this end, south is up this end. The ore bodies again shown to you as the hatched grey colour. The colours are the oxygen isotope anomalies. So what we see here is a very clear gradient towards the ore bodies. The ore bodies are surrounded by the most oxygen isotope altered rock, and there is a clear gradient from surface down towards the ore bodies that extends, in this case, almost 1.5 to 2 kilometers to the ore bodies. So the point of this is that you can be exploring and you can determine whether you are getting closer to a fluid flow source and a possible ore body. There's a clear gradient, and Chris Waring actually calculated a delta, as you know, gradient per distance that would tell you whether you were getting closer to the ore system or not. We can have a look here at a series of now cross sections rather than long sections. We'll start off with this B to B prime section line. And what you're seeing in here are north of the main deposits. We see that there is still clearly a gradient in towards the system. So the fluid flow is probably following the Paru fault, but we see a relatively muted halo, or sorry, a relatively narrow halo of more intense alteration. So probably more focused fluid flow. When we come to the south here and we go across some of the main ore bodies, we see that halo becomes broader, and it seems like this is almost certainly linked to some of the structural discontinuities that have been mapped. So in this case now, the fluid has no longer been probably focused along the faults. It's been forced out into the hanging wall, and that's likely one of the reasons why the ore deposits are forming in these locations. There's more intense fluid rock reaction that's occurring. And as we come down south of the ore body, what we see over here is now this very interesting anomaly, no known deposit here, although an area of significant interest, with a very intense oxygen isotope alteration halo setting off to the east or to the southeast of the main ore bodies. And if you were to squint at this and you put on a structural geologist framework, you might just about want to project some of that stuff along strike, but perhaps I need to have another beer before we really talk about that. So to summarize the isotopes, I won't talk about it for any longer so we don't go on all night. We get these clear, distinctive gradients towards the ore bodies in the oxygen isotopes. So that's all well and good, but what else can we do to help us within these systems? Now, one of the other things we can actually utilize is the whole rock lithogeochemistry in the Urquhart Shale. So if you go and collect 4-acid ICP-MS data, and that's really important here, we need the 4-acid, a near whole rock digestion to allow us to see this. Aqua regia data won't allow us to dissolve this. One of the things that's been recognized and was described by Ben in his PhD thesis is that we actually get a very distinctive potassium anomaly sitting around the ore bodies and around the fluid flow zones. Now, this data in this case has been creed up against the oxygen isotopes. Okay, so what Ben was trying to do here was to show you that the potassium anomaly, okay, so remember the oxygen isotope anomaly has gone probably 1.5 to 2 kilometers. In this case, the potassium anomaly is going somewhere on the order of perhaps 1 kilometer away from the main ore bodies and is forming this distinctive potassium anomaly, positive potassium anomaly away from the deposits. And close to the deposits, we actually form a potassium over aluminium low. We're dissolving potassium-bearing minerals in an acid environment, and we're mobilizing that potassium outboard where it gets neutralized and deposits as potassium feldspar. And so Ben's actually been sort of plotting that up to show you what that looks like here. So the colors in the background are the oxygen isotope anomalies. The dots you can see down the drill holes are the potassium over aluminium results. And this, again, we're looking on this southerly section here, this D to D prime section, so away from the known ore bodies, which is one of the places where we could get the geochemical data, because they only started collecting this routinely in the last couple of years. But what you can see here is that in this part of the section where the isotopes aren't doing very much, we have essentially background potassium over aluminium values of about 0.3 to 0.5. In the most isotopically intense part of the altered part of the system, we see this these depleted values. This is associated with chloride alteration. And then as you go outboard, you start to run into significantly elevated, so greater than 0.5 potassium over aluminium ratios of basically potassium-bearing rock. And that actually extends in this case all the way up to surface. So you've got this distinct potassium anomaly. So while we have an isotope tool that's clearly very effective, there's also a geochemical tool, the much more conventional lithogeochemical tool that can be exploited in the Mount Isa systems to help you navigate through them. And you can most probably pick this up. It hasn't been proven or tested by Ben, but you could almost certainly pick this up using a portable XRF down the drill holes directly while you're waiting for the assay results to come back from the lab. You'd simply go looking for high potassium over aluminium values. You could do it probably straight on the drill core, because you've got nice fine-grained shales that will respond pretty well to a portable XRF. They're nice and homogeneous. So zones of potassium depletion and then potassium enrichment outboard from that. So if we come all the way back to the reaction front theory that I introduced at the start of the talk, we can now map out a whole series of reaction fronts in these Mount Isa systems. We have a potassium front. Sorry, we have a copper front. Now, of course, that's our ore. That's what we want to find. We have around that ore body, we have a silicified core, which is often very proximal to the high-grade ore. Around that, we have the development of chloride and talc alteration and a zone of calcium and potassium depletion. So it's, again, something we can possibly pick up in logging. Certainly, we can pick it up geochemically. Outboard of that in the blue, there's a potassium anomaly, potassium over aluminium high that we can go and map out. And then around that, most distally, and that's probably taking you out literally kilometers, so it's the biggest target to look for, and it gives you gradients within it, is the oxygen isotope reaction front. So you can use a combination of tools, your oxygen isotopes, your whole rock lithogeochemistry, possibly logging of vein types and vein mineralogy to help you vector within a Mount Isa style system. And these approaches and these concepts are very transferable into any other carbonate-hosted deposit type. And so if I bring you back to the original diagram that we drew looking at reaction fronts, you could draw the same sorts of alteration profiles for a Mount Isa style system where you can develop them for your rock type. And you should now be able to use the distances that these fronts are propagated. Are they all nested on top of one another, as in this case here, which means there hasn't been much fluid flux, or are they strung out over distances of hundreds of meters or potentially kilometers, telling you you're looking at a very big hydrothermal system. So this theory that's been developed, the reaction front theory, appears to be extremely applicable when applied across a range of ore deposit types. Some of the Carlin systems I showed you earlier, and certainly appears to hold up very well in Mount Isa. Now I'm just going to touch very quickly. I don't have time to go through this in detail, but the final, I guess, stretch thing, or something that we've been actively working on, is trying to think very hard about this thermal part of the system. Now we can map the oxygen isotope exchange, but could we map the thermal footprint of these systems, which may go even further? And this is very much a work in progress, but there are some interesting new tools that have emerged that now potentially allow us to do this. So the concept of this is very simple. Fluids that are cool and sinking, such as this model that's shown to you here, will depress the isotherms. Fluids that are warm and upwelling, like we would see in a geothermal or an epithermal environment, and perhaps somewhere like Mount Isa, or certainly a porphyry system, are warm and upwelling, and they drag the isotherms upwards. So if we could routinely and robustly map isotherms within ore deposits, particularly carbonate-hosted deposits where we don't have good mineralogical proxies for temperature as we do in a porphyry system, this would be quite a powerful tool. Now, you could try to do fluid inclusion. Sometimes in carbonate-hosted systems, you get nice ones, not very often. They're normally pretty painful. If not, then you want to get a temperature structure. We normally rely on index minerals or phases to do this, things like the recognition of biotite or recognizing illite-smectite transitions, for example. But those, as you can see from all the overlap here, are not particularly robust. They're not particularly distinctive in terms of temperature. So certainly they might say, yep, biotite, you're hot. But they don't tell you if you're at 270 versus 350, which is what you might want to sort out. Now, in the last few years, continuing on my cryptic theme, and this is going to be even more cryptic, there's been a very interesting new tool that's emerged, of course, out of the paleoclimate world, but we can corrupt that to do mineral exploration, I think, called clumped isotopes. Now, I'm not going to get into any of the details. What you need to know is this is a very difficult measurement to make at the moment, and we need to make it simpler and faster if this is ever going to be useful. But what this allows us to do is to directly measure a carbonate mineral. I apologize for the graininess of this figure that I had to blow up out of a PDF. But you can measure what's called this delta 47 number, which we do in a sophisticated piece of a mass spectrometer. And we can tell you whether that carbonate is a 200-degree carbonate, a 300-degree carbonate, or a 100-degree carbonate, and potentially with considerably more precision than that. Now, the thermometer probably stops being useful at about 350 degrees, but below that, which would be the range of temperatures of interest to something like Mount Isa, and indeed a number of other systems, we get some very interesting variations in this clumped isotope value. Now, we did some proof of concept work published in a paper with a student a couple of years ago, essentially demonstrating that this potentially worked. But Ben also collected some clumped isotope data from Mount Isa, and I find this particularly interesting. And I collected just enough data to not really prove that it works, but to show that that's kind of intriguing. So I already showed you these section lines, which are these slices, these oxygen isotope slices through the deposit. But what we're going to show you now are some of the clumped isotope results. So this is a sort of model that Ben had come up with from a fluid flow perspective, that in this case, fluid's going up the Paru fault, and in this case, it's sort of streaming off above the main ore bodies, and there's this very interesting zone over here of sort of active exploration intrigue. So Ben went and measured some stable, some of these clumped isotope values. So without going into the detail of any of this, what he showed is that the clumped isotope temperatures sitting in and above the major Mount Isa ore bodies are hotter, so more like 300 to 350 degrees, than the fluids, than veins sitting to either end of the main system, which are around 200 to 220 degrees. So hot are fluids over the main ore body, cooler fluids at either end. Now, This is actually consistent with fluid inclusion work that Chris Heinrich did in the 1980s, where he noted these temperature variations and he couldn't explain them from a fluid inclusion perspective, and he thought that it must be a pressure control. But our follow-up work with the clumped isotope actually suggests that Chris's measurements of the fluid inclusions were likely entirely accurate, and this isn't a variation in pressure. This is a genuine variation in temperature across the deposits, and the major upflow zones, or our major interpreted upflow zones, have the highest temperatures, which you might expect from an upwelling fluid perspective. So this is not a laterally isothermal system. So if you could march through an Eisen-style exploration system, or indeed many other carbonate systems, and pick out the hotspots with a relatively low number of samples, this could be potentially quite a powerful exploration technique. But as I said, a lot more work is needed. So we can now potentially tell you, are you looking at high temperature or low temperature carbonate veins, and look for temperature gradients vector towards the highest temperature part of the system, and link that back to your much larger conventional isotopic data set to help you figure out what's going on. And then the ultimate question, and one that certainly has not been answered by us or to my knowledge anyone else, is can we map heat diffusion gradients outside those zones of advection? Could we actually sniff out hotspots where no fluid was leaking? And that's a very intriguing concept, but a lot more work needs to be done. So in summary, we've now been working on a whole series of these tools to help us recognize the cryptic signatures of these deposits, integrating stable isotopes, lithogeochemistry, ultraviolet fluorescence, as a rather attractive picture on the right-hand side shows you. And you can integrate these tools. Some of them I think are standard, or they are standard industry practice. In the case of lithogeochemistry, I'd argue the stable carbon oxygen isotopes should be standard practice if you're exploring in carbonate-hosted terrains. And many of these tools are suitable for uptake directly by the minerals industry. So by applying this research, we're both figuring out these cryptic halos. So we're, in this case, genuinely sort of revealing this in these invisible styles of alteration that we can see. And I think we'll see a real explosion of data in the next few years that's going to enable us to harness this understanding, and hopefully enable us to be more effective explorers in carbonate-hosted terrains, because we have a whole bunch of hungry beasts around the world in terms of energy demand, and we're going to have to feed them rocks. So we have a real challenge in front of us. So thanks very much.
Thank you so much, Shaun. That was wonderful.